Something extraordinary is happening inches from the heart of our solar system, and we cannot see it. A visitor from the space between stars is hitting peak activity exactly while Earth is blinded by sunlight. The moment of maximum heat arrives, and our cameras go dark. That is the paradox. An object becomes loudest just as the stage lights drown it out. What changes in the dark can change the story. When it reappears, it may not look the same. Stay with me as we chase it through the glare. Like and subscribe so you do not miss what comes next. Start with the simple truth. 3i Atlas is near closest approach to the Sunday astronomers call this perihelion. The distance is about 1.4 astronomical units, which sounds close, yet it is actually just inside the orbit of Mars. An astronomical unit is the average distance between Earth and the Sunday. We use it to turn impossible scales into something you can picture. At perihelion, sunlight roars across the surface and the object sheds material into space. That shedding is normal for a comet. The weird part is the timing of our view. From Earth, the sun's glare blocks the action right when it gets most interesting. What does heat do to an interstellar visitor? On a comet, sunlight does not melt into liquid the way it does in a kitchen. Space has no air and no pressure. So many ices skip the puddle state. They jump straight from solid to gas. That jump is called sublimation. Imagine dry ice at a concert throwing off a ghostly fog. Now replace the stage with sunlight and vacuum. Gas pushes out of the surface and carries dust with it. The blurry halo around the solid core grows. Astronomers call that halo the coma. The coma is not decoration, it is evidence. It tells us what the object is made of and how violently it is venting. Then comes the tail, which is not a single thing. Part of the tail is dust that sunlight can push, grain by grain, into a streaming fan. Part of the tail is gas that interacts with charged particles in the solar wind, the constant outflow from our star. In strong light and strong wind, the coma lengthens and the tail points away from the sun like a windsock in a steady breeze. The stronger the energy, the louder the shape. Tail geometry is a living readout of physics. It changes with distance, chemistry, and time. If we could watch the tail of 3i Atlas at the very peak, we would read a moving graph written in dust and ions. But Earth is in the worst seat in the house. Picture the sun as a floodlight at center stage. Our planet sits in the front row, dead center, with the lamp pointed right at our eyes. The visitor strolls through the spotlight, and we are blinded by brilliance. Ground telescopes cannot fight that. Even space telescopes must respect the hazard. To protect cameras and keep stray light out of sensitive optics, they avoid pointing too near the Sunday. That is why a blackout window opens around perihelion. It is not a conspiracy. It is geometry and safety. If you are thinking that sounds frustrating, you are right. Investigation thrives on continuity. Here, the timeline breaks, so we switch tactics. Instead of one perfect view, we stitch together what the story looked like on the way in and what it will look like on the way out. Before the blackout, we saw 3i Atlas begin to wake far from the sun, when most comets are quiet. We measured light brightening faster than expected and a coma taking shape early. After the blackout, we will measure again. We will test whether the chemistry flipped, whether the tail settled into a textbook form or kept misbehaving, and whether the core looks eroded or refreshed. This is not just a patience game. It is an experiment with a built-in control. Heating ramps up until perihelion, then ramps down. If a pattern that looks strange on the way in repeats on the way out, we learn something deep about what is inside. If the pattern changes, we learn how sunlight sculpts a traveler from another star. Both outcomes are science moving forward. Both outcomes raise better questions. And the clock is ticking toward the moment the curtain lifts, when our instruments can look again without being overwhelmed. You may ask why the distance matters if the sun is so bright. Think of heat as a dimmer switch. 1.4 astronomical units is not a blaze of pure fire, but it is a strong push. Many ices, including carbon dioxide and water, respond differently to that push. Some boil away easily, some hold tight until the oven is hotter. The order in which these ices unlock controls the coma's chemistry and the tail's shape. That is why scientists care about exact distances and the timing of changes. They are not trivia. They are clues to a recipe written in ice and rock. There is also a quieter reason this blackout fascinates scientists. We almost never get to watch an interstellar comet this clearly at all. Only a handful have ever been seen. Each one is the control experiment the galaxy sends us, a sample collected in a different star system and delivered to our door. 3i Atlas brings its own rules and its own surprises. The blackout window is not a void. It is a cliffhanger. When the glare fades, we will see what the sun carved, what survived, and what stories the tale still wants to tell. Stay with this investigation. When the visitor steps out of the light, we will be there to read the changes line by line, and you will have the front row back. Rewind to the night the survey telescopes did what they do best. The Asteroid Terrestrial Impact Last Alert System scans for tiny movers against a background of still stars. A dot slips between frames. At first, it is logged like thousands of routine detections. Then the numbers refuse to be routine. The motion is too quick for its distance. The fit to a bound orbit does not work. A team that plans for rocks from our neighborhood has stumbled on a messenger from somewhere else. Speed is a language in space, and 3i Atlas speaks it loudly. Earth loops the sun at about 30 kilometers per second. That is already fast enough to cross a continent in a blink. Closer in, planets must sprint even harder to avoid falling inward. Yet when 3i Atlas was still out near the orbit of Jupiter, roughly 4.5 astronomical units from the sun, its pace was clocked near 58 kilometers per second. That is absurdly fast for that distance. Plug those values into gravity's math, and the result is not a closed ellipse. It is an open curve that never turns back. Astronomers call that path a hyperbolic trajectory. In plain terms, the sun's pull is not strong enough to capture the traveler. It dives in from the deep, swings through the inner system like a skier carving a wide gate, then aims back out to the interstellar dark. Hyperbolic is the unambiguous signature of an object that came from beyond the sun's family. The solar system did not birth it. The solar system can only bend it. This is not our first interstellar guest. A few years ago, Oumuamua flashed by in mysterious silence, oddly shaped and coy with its chemistry. Later, Borisov arrived, behaving more like a classic comet with a familiar tail and a textbook response to sunlight. 3i Atlas stands apart from both. The possible size is larger, up to around 5.6 kilometers across rather than a few hundred meters or about 1 kilometer. The speed is higher, not by a little, but by a gulf that matters for how forces act over time. And then, there is the direction of arrival, which may be the strangest part of all. To understand the oddity, flatten the solar system in your mind. Imagine a cosmic record made of planets, moons, and smaller debris, all spinning within a thin disk around the sunday. That disk is the plane of the ecliptic. Most of the action happens close to that plane because everything formed from the same swirling pancake of gas and dust. A few orbits lean away. Pluto, for example, tilts by about 17 degrees. Many comets cut across at steep angles and dive above or below the disk, like needles through cloth. 3i Atlas did not. It slid in almost along the disk itself, only about 3 degrees off the plane. That geometry feels like a sideswipe, not a head-on collision. Think of two highways merging. Oumuamua and Borisov approached more from above relative to the disk, so our encounter felt like an oncoming lane. 3i Atlas arrives in the traffic lane itself, the kind of pass that makes you hold your breath. Did we get lucky? Is this the only line that let us notice it early and watch it evolve for months? Or is there a deeper story about how interstellar objects are delivered to us along preferred paths by the combined tugs of stars and galactic tides? The coincidence stack keeps growing, fastest ever measured inside our system at that range, possibly larger than the prior two visitors by a wide margin. And, threaded into alignment with the planetary disks so neatly that the tilt is barely there, any one of these would be remarkable. All three together create narrative gravity of their own. The mind wants to connect them, to see a pattern that explains speed, size, and alignment with one generous idea. Caution is wise, patterns are seductive. The evidence says only this so far. The object is real, the measurements are real, and the strangeness is not a trick of perspective. Still, strangeness is a gift when you are trying to learn. Higher speed means less time under the sun's heat, yet the incoming leg already showed unusual behavior. Larger size means more surface area to vent, and a bigger reservoir of ices and dust to interrogate. Shallow tilt means the visitor's path crosses the same plane where most of our instruments and spacecraft operate, which raises the odds that cameras at the right place and time can actually see something meaningful. Each contrast becomes leverage. Each contrast increases the chance that this single pass will teach us more than a decade of routine comets. When survey teams realized what they had, the follow-up was immediate. Telescopes on multiple continents and in orbit adjusted priorities. Positions were refined, brightness measured, models updated, the hyperbolic shape locked in, the predicted miss distances firmed up. 3i Atlas would never come particularly close to Earth. but it would skim by Mars on its way inward and later swing near Jupiter on the way out. That set the table for opportunistic imaging from robotic eyes already in place. The alignment that felt uncanny also felt useful. The stage was lit. If only the star of the show would keep to schedule. Speed, size, alignment. Those are not trivia you memorize for a test. They are the opening chords that tell you what genre you're hearing. Fast puts us in the key of Interstellar. Big says the signal will be loud enough to hear. Aligned says the microphones are, pointed the right way. From there, the melody becomes chemistry, light, and time. We have already heard notes that do not belong to the usual song. We are about to hear the chorus. The first big clue arrived as a change in brightness. The transiting exoplanet survey satellite watched a small patch of sky for about a month, and 3i Atlas drifted through the field. As it moved one astronomical unit closer to the sun, astronomers expected a modest increase in reflected light. Instead, the brightening jumped by roughly 5 times what simple geometry predicted. That jump shouted one conclusion. This is not a bare rock. This is an active comet throwing a cloud around itself. Brightness in astronomy has a careful name. Observers call it flux. Think about the sun at noon on a clear day, then imagine standing the same distance from a blast furnace that is twice as close. Nothing about the furnace changed, yet it feels far hotter. Your distance changed the energy that reaches you. Flux is that feeling turned into a number. For 3i Atlas, the numbers said the surface was venting gas and dust into a halo that made the object reflect far more sunlight than a solid core alone ever could. Now comes the twist. The scattered light from that halo carried a fingerprint that did not look like the usual solar system mix. Polarization is a way to describe the direction that light waves wiggle after bouncing off tiny grains. Most comets and asteroids lean toward a positive pattern that matches side scattering. 3i Atlas leaned hard the other way. It showed a strong negative polarization, the most extreme on record for a body like this. In plain language, the grains in that halo were arranged or sized or coated in a way that sent light back to us with an unexpected orientation. Polarization sounds abstract until you place it in your hand. Hold a piece of black glass at different angles and notice how glare changes. The effect depends on the surface and the light path. Replace the glass with dust rich in volatile coatings from another star system, and you get a different glare profile. That is why scientists did not dismiss the result as a measurement quirk. The repeated readings said this comet carries material or structure that does not match our local recipes. Strange light was the first confession from a very old traveller. Chemistry delivered the second confession. Far beyond the orbit of Jupiter, where most comets are still slumbering blocks of ice and rock, the halo of 3i Atlas was already strong. The culprit was not water. It was carbon dioxide, the same stuff that makes dry ice fog on a theatre stage. Carbon dioxide turns to gas at a much lower temperature than water ice. Out in the cold, sunlight was still strong enough to knock carbon dioxide molecules loose. As they rushed away, they dragged fine dust along and built a halo long before a typical comet would wake. That early carbon dioxide wake-up changed the choreography near the Sunday. As the visitor fell toward the orbit of Mars, the temperature ticked higher and the screenplay flipped. Water finally joined the outgassing in a dramatic surge. Observers compared the rate to a fire hose opened wide. For a while, the outflow of water vapor looked larger than standard models would guess at that distance. The halo chemistry was not static. It was a relay race, carbon dioxide sprinting first, water pounding in later with heavy steps. Then the metals complicated everything. Over the summer, spectrographs teased out a whisper of nickel atoms in the halo while iron stayed silent. Nickel and iron are usually born together in the hearts of dying stars, and they are found side by side in meteorites and planetary cores. Seeing one without the other felt like a magician's misdirection. Some suggested that jets of gas might be lifting nickel off specific patches, while iron remained locked in grains that needed more heat. The evidence changed again as few weeks passed. By early autumn, iron lines appeared, and the nickel-to-iron balance slid toward the familiar. The trick was revealed. Nothing supernatural was required, only timing and temperature. If you track the pattern, a theme emerges. Weird first, familiar later. Early activity dominated by carbon dioxide when distance was large. An optical fingerprint that bent the rules of polarization. A metal imbalance that corrected itself as sunlight did more work. Each oddity tempted a wild explanation. Each time the next set of observations tugged the story back toward normal physics, reshaped by unusual starting conditions. That is not a disappointment. That is how real puzzles behave under persistent light. There is a deeper lesson in this timeline. Many models of comets in our neighborhood start with water ice as the star of the show. 3I Atlas forced a new opening act. When carbon dioxide leads, the halo forms farther out, and that means tail geometry, brightness curves, and even the direction that dust accumulates can look wrong at first glance. Put the same object under stronger wind and deeper heat, and the picture snaps into a shape we recognize. Sequence matters. Order of activation is destiny. None of this should be read as the end of surprise. When the object re-emerges from the sun's glare, we will look for the echoes of that early behavior on the way out. If negative polarization persists as the halo thins, then the grain properties are intrinsic rather than a transient byproduct. If water stays high while carbon dioxide fades, then the surface layers have been overturned to expose new ice. If the iron to nickel balance stays steady, the metal mystery may be closed. And if any of those threads refuse to settle, the chase continues. The light misbehaved, the ices woke early, the metals played coy. Taken together, these are the quirks that make a single pass worth months of attention. They are not random noise, they are footprints left by an origin. Story written in a different corner of the galaxy, then edited by sunlight from our own star. 3I Atlas is not here to obey our expectations. It is here to test them. That is the real drama behind the numbers. The first tail broke a rule in plain sight. Instead of streaming away from the sun like a windsock in a steady breeze, the early plumes seem to pile up toward the light. That looks like defiance, yet the explanation is patient and mechanical. Far from the sun, the solar wind is gentle. Carbon dioxide began to lift off the surface long before water stirred. Gas boiled off the warm face and dragged dust into a sunward haze. With little wind to sweep the particles back, the halo grew lopsided toward the heat. The comet was not ignoring physics. It was living at the edge of two regimes where rules change with distance. As 3I Atlas fell inward, the environment stiffened. Radiation pressure rose, the wind picked up, and the lopsided blur reorganized into a short fan pointing away from the Sunday. That pivot is a lesson written in motion. Geometry follows chemistry. Start with carbon dioxide leading, and you paint a soft glow on the sunlit side. Add water and stronger wind, and the brushstroke flips. The same object can draw two different pictures within a few weeks, not because it became a different comet, but because the dial on the furnace turned. If tail behavior is the handwriting of a comet, then we want the cleanest sample we can get. That is why the path near Mars mattered so much. The object passed within a fraction of an astronomical unit from the red planet. We have more cameras at and around Mars than any world except Earth. Opportunity was built into the orbit map. Perseverance stared long enough to accumulate light, 30-second exposures stacked into a streak that crossed the Martian sky. The result is not pretty. Rover cameras were not designed as deep sky observatories, yet even an ugly streak can prove that a plume exists, and roughly how bright it is. The orbiter images did better. The European mission that circles Mars carries instruments that could turn the streak into a small smear with edges. From that vantage, the plume looked real rather than imagined, the fan shape starting to assert itself. It was not enough to see a sharp boundary between solid core and coma. It was enough to anchor models so that later measurements have a place to land. In planetary science, you often get breadcrumbs rather than cake. You learn to be grateful for crumbs when they fall at exactly the right moment. There was hope for one more step. The Mars Reconnaissance Orbiter carries a powerful telescope that has mapped boulders on the Martian surface from orbit. Point that eye at a passing comet, and you might separate the inner coma from the glare and watch structure resolve. Then real life walked on stage. A government shutdown in the United States sent many teams home and delayed processing and release of non-essential images. The silence might mean no image was taken. It might mean an image exists and sits uncalibrated on a server. Either way, the result is the same for viewers. The most capable nearby lens did not deliver a picture when curiosity was white hot. Absence is its own character in this story. The perihelion glare blocks most Earth-based views at the exact moment when tails are usually at their most dramatic. Space telescopes that could tolerate the brightness are designed to avoid the sun for safety. Mars had the angle, offered proof of a fan, then left us staring at a closed curtain where the best potential image might have appeared. The shape-shifting tail becomes a rumor you can almost touch. That tension is not a failure. It is the cost of doing astronomy near the spotlight that keeps us alive. So, we study the quiet details that remain. How fast did the apparent length of the fan change as the object crossed the Martian neighborhood? Did the brightness slope steepen in a way that lines up with water taking the lead? Did the angle of the fan match the local direction of the wind from the sun at that hour? Each modest check is a thread pulled tight across a gap in the photo roll. When the object rounds the sun and enters a safer pointing zone, we will be ready to compare those threads against new images that show the fan cleanly. There is one more reason to care about the missing pictures. A tail is more than a postcard trail behind a traveller. It is a lever. With a good view, you can estimate how much mass is leaving the surface. You can search for narrow jets that betray vents and fractures. You can watch the fan pivot day by day and back out the spin of the core. Each of those measurements turns the mystery from a single dramatic silhouette into a physical object with numbers that stand up. That is the power of a photograph when it arrives at the right moment. We did see a tail point the wrong way. We did watch it correct. We did catch it near Mars, with instruments that were never meant for this chase. We did not get the sharp image that everyone wanted. The next act belongs to geometry and patience. When the glare softens and pointing restrictions ease, the cameras turn back on. The fan will tell us what the furnace did to the surface, and whether the object has settled into a steady rhythm, or if it still prefers to surprise us. To understand a traveller, you map the road behind it. 3i Atlas does not point back toward our neighbourhood. It points toward the crowded brilliance near the centre of the Milky Way, then slightly above or below the thin lane where most stars whirl. Astronomers call that quieter region the thick disk. Fewer supernovas shatter it. Fewer close encounters rip new paths through it. Objects can drift there for eons with their original textures preserved. That origin hints at age. If 3i Atlas formed in a calm pocket of the thick disk, it may be older than Earth by billions of years. Some estimates stretch to about 7.6 billion years, which makes every grain in the halo a time capsule. We are not just watching a comet. We are reading a record written before our planet hardened from molten rock, a record that kept its shape by staying out of the worst traffic lanes of the galaxy. Rewind the clock by 10 million years, and you get a travel diary of close calls that never got very close. Models identify roughly 93 stars that the comet passed within a broad neighbourhood of during that span. The nearest approach in that list is on the order of 0.3 light-years, which is 63,000 astronomical units. For scale, that is far beyond the distant shell where our own comets hibernate. The lesson is humility. Interstellar space is so empty that even a list of near misses reads like a census of nobody home. Now, return to our present. After the perihelion blackout ends, the geometry improves for Earth-based instruments. The object reaches its nearest distance to Earth's orbit around mid-December at roughly 1.8 astronomical units. That is still far, yet close enough for a clear test of how the coma and tail have changed under peak heating. A few months later, the path carries 3i Atlas within about 0.36 astronomical units of Jupiter. That is close in Jovian terms. It also means one last good chance for a camera that has already delivered years of insight. Juno is the quiet hero in that plan. The spacecraft loops around Jupiter on a long oval, stealing glimpses of the planet's storms and the strange worlds that circle it. If timing aligns, Juno can pivot to catch a final portrait of 3i Atlas on the outbound leg. The image will not be glossy poster art. It will be a data point in a chain, a way to watch activity decline as distance grows, a way to check whether the tail's direction and brightness match what models predict as the furnace cools. The outbound chapter will test more than pictures. If the negative polarization persists while the coma thins, that points to grain properties baked into the material rather than a temporary coating. If water remains strong compared with carbon dioxide, then the surface layers may have been overturned to reveal new reservoirs. If iron and nickel keep their now normal partnership, the early metal imbalance can be chalked up to timing. Each if gives us a clean pass or a fresh question. Both are wins. Both turn rumour into measurement. Where it came from, and where it is going, anchor the end of this story, yet the meaning is larger than one track through the inner system. Interstellar visitors are control experiments that nature runs for free. They are samples collected under other suns and handed to us without the cost of a mission that would take longer than a human lifetime. When a sample behaves like our local comets, we learn that some rules travel well. When a sample misbehaves and then slowly drifts toward normal as conditions change, we learn which rules come from environment rather than birth. 3i Atlas was loud in its strangeness. A coma led by carbon dioxide far from the Sunday. An optical fingerprint that bent towards strong negative polarization. A tail that piled sunward before the wind could push it back. Then came the pull toward familiar behavior as heat rose. Water surged, the tail flipped. metals balanced. That arc is not a disappointment. It is a lesson about sequence and context. Change the order of what wakes, and you change the picture you paint. There is a human dimension as well. This object arrived when our instruments were ready to listen. The alignment in the plane of the planets placed it where our cameras can work. The pass near Mars let robotic eyes prove the plume existed. The march toward Jupiter could give Juno a final look. Across that path, we felt the limits of geometry and bureaucracy, the glare of the sun, and the pause of a shutdown. Even with gaps, the story holds. Enough notes were recorded to hear the song. Soon the visitor will fade. The coma will collapse back toward the core. Dust will settle onto a surface scarred by jets and warmed by a star it will never see again. We will fold the light curves and polarization plots into papers and models, then wait for the next courier from the dark between stars. What we learned here is simple and deep. Normal is a spectrum, not a cage. The universe is generous with surprises and patient in the way it reveals them. We only have to keep looking and keep listening when the chorus returns.